In this lesson, we're going to look at 7.3 reaction quotient and equilibrium constant. So this learning objective states that we should be able to represent the reaction quotient as either a QC or a QP, so again, concentration or pressure, for a reversible reaction, and the corresponding equilibrium expression, Kc equals QC or Kp equals QP. So the reactant quotient, let's talk about what that is. So that is denoted by QC, and it's going to describe the relative concentrations of reaction species at any time. So when we looked at K in 7.1 and 7.2, that was at equilibrium. A Q, the reactant quotient, is at any time, whether that time actually be equilibrium or it's the time leading up, okay? So for gas phases, in this case, we would have QP. So the reactant quotient tends towards the equilibrium constant. So you can compare K and Q to see, hey, where are we at this specific time? So if you figure out what your Q is and it equals what K is, guess what? You're at equilibrium and everything's great. Now let's say we do it and K is less than Q. Like I taught you with the arrows, but you have to write K first when comparing. If K is less than Q, you need to go in the reverse direction to reach equilibrium. So again, comparing K and Q can tell you like, hey, where are you at right now? Do we need to make more reactants? Do we need to make more products? In this case, we need to go to the left. What is to the left? The reactants. So going in the reverse direction, we can make more reactants to get us to equilibrium. And then vice versa, if your K is greater than Q, draw that little line right there that tells us to go in the forwards direction. And again, this is to reach equilibrium. And so here, what's in the forwards direction? What's to the right? We need to make more products to get us to whatever K is. So if you look at this graph, K at this point in time, this is where K is, because you can see this is where it's staying constant. Everything to the left, this would be what Q is. Q is at any time. Now, Q could be right here, but we wouldn't know until we were able to compare K and Q, whatever K's value is. But generally, Q represents a lot of the time the initial part of the reaction. But again, this is most of the time, not always. So the reactant quotient does not include substances whose concentrations or partial pressures are independent of the amount. So just like K, do not include solids and liquids. So let's look at this right here. So Q, like we just learned, is the reaction quotient. K is the equilibrium constant. And so Q is the concentration of species at any time, while K is the concentration of species at equilibrium. Now, I do want you to put here that Q is written just like K. So just how you learned about K doing the concentration of products raised to their coefficient divided by the concentration of reactants raised to their coefficient, same thing. And so again, to try to talk about QC versus QP, QC is systems with solutions, while QP is systems with gases. And so again, C is concentrations, molarity, big M, while gases, these QP is pressures, which you'll look at ATM, torr, etc. Mostly atmospheres and torr. Now, one thing I do want to note, because this is very important information, it's not assessed on the AP exam, but I remember using it a lot in college, and it's very good to know. there is a equation to convert between Kp and Kc. Because remember, Kc, you can put gases in there. Okay, because gas is talking about the amount of moles per that volume. So it's not necessarily just solutions. Solutions being AQ, it also can use gases in A, Kc, Qc, whatever. So the equation is Kp equals Kc, parenthesis, R for the ideal gas law constant, T for temperature, raised to the power the change in N, where change in N is going to be change in moles. So the moles of the product minus the moles of reactants. So here for that case, you would just look, you would count the coefficients on the product side and count the coefficients on the reactant side and take the difference of that. Now again, don't need to do this on the actual AP test or my class, but it is very good to know that there is a relationship between Kp and Kc.